Okay, now we have to consider again some concepts relating to CMOS logic. They should be a concept that you already know from the course in digital electronics in the undergraduate degree, but I will try to at least refresh some of the concepts just to be sure that we at least use the same language. And in order to do that, I need to start from the basic CMOS logic gate. That is the inverter. So some of the things that I will tell you are already very clear to you. My main point is just to let's say highlight the concepts that are important in order to understand why the semiconductor industry has moved towards these smaller and smaller dimensions for the transistors. What's the reason? What is the advantage? What is the cost? Okay, and in order to do that, we need to, let's say, derive some expressions for the maximum clock frequency, for power consumption, and so on. So some of them are already known to you, but let me just go through them all. So the CMOS inverter is a very simple circuit. It's basically consisting of just one Nmos transistor and one Pmos transistor. This is the Pmos. This is the Nmos transistor. Of course, this is the input, this is the output, this is ground, and this is the supply voltage. Let's call it VDD. So it's probably also important to write down the current voltage characteristics for Nmos and Pmos in all operating conditions. Let's start from the Nmos first. So as you know, there are three operating conditions. One is if VGS is smaller than VTN. VTN is the threshold voltage of the N transistor. In this case, the transistor is off. Of course, it means that the ID is equal to 0. Okay? This is something that you already know. Then, if VGS is larger than VTN, the transistor is on, because we have a channel formed below the gate dielectric, but there are two possible situations. One situation is that in which VDS is smaller than VGS minus VTN. In this case, we are in a so-called ohmic region or triode region. In the ohmic region, and this is the reason why it's called ohmic region, the current between drain and source is more or less proportional to the voltage between drain and source, as in a resistor. And indeed, we have an approximated IV characteristics like this. We have something like Kn times VGS minus VTN times VDS. This is the linear part, and then there's a quadratic correction also, that is something like this. Okay, we sometimes typically discard this quadratic term and we only remember the linear term. So we have EDS is proportional to VDS as in a resistor. The resistance is inversely proportional to VGS minus VTN. Okay. In terms of names, this part is called this term is called also overdrive. Or to be more precise, gate overdrive, because it's the difference between the gate to source voltage and the thresher voltage. It's the part that we have above the thresher voltage. Okay. This constant is a property of the transistor and partly depends on the geometry, partly depends on the material. Basically, it is W over L times mu n times Cox, where actually the Cox is the oxide capacitance per unit area, so it is epsilon R times epsilon 0 over T ox. Okay, let's see what these terms are. These are important because most of the things that we will derive today will depend on these quantities. So I mean, I even if you already know this concept, I'm going slowly to let you at least let's say absorb the nomenclature. This W is the width, the channel width of the transistor. This L is the length. This mu n is the electron mobility. So it's the mobility of electrons in the channel. And of course, we're interested only in the mobility of electrons because we're talking about the Nmos. Okay. Then this Cox is defined here. This epsilon R is the electric constant of silicon. The electric constant of the silicon oxide, for example. The electric constant of the oxide in the MOS structure, metal oxide semiconductor. And this Tox is the thickness of the oxide. Okay, this part also is also in this part is important to keep in mind what are the functional dependencies. You see, this Kn is something to which the current is proportional. So the current is proportional to Kn, which in turn is proportional to the mobility, to the dielectric constant, to the width, and it is inversely proportional to the length and to the oxide thickness. Even if you don't remember the exact formula, it is extremely important to remember the dependencies, the functional dependencies. What increases if something else increases or decreases. Okay, and then there's the third operating condition, the third bias condition, which is the situation in which, of course, VGS is larger than Tn, is a non-condition again, but VDS is also larger than VGS minus VTN. In this case, what we have is another expression. As you remember, we are in saturation region. And in this region, IDS depends almost only on the overdrive, because it becomes something like Kn over 2 times VGS minus VTN to the second power. Okay, so at the first order, there's no dependence on VDS. In practice, as you know, there is some dependence, but for the moment we're not explicitly considering it. Okay. All the quantities have been already defined. They are not so important for us at the moment. Now, so the three operating conditions are 1, 2, and 3. Right? What are the conditions important for us? Well, actually, as one always says, in digital electronics, the two most common situations in which a transistor is operating are the first two. So basically, a transistor is in the off state, so it behaves as a switch turned off, or it is in the on state, so it operates as a switch in short circuit. This is true, of course. In practice, also, the saturation region is important, because when we have a switching and the transistor commutes from switches from the off state to the ohmic region, typically it passes through the saturation region, and therefore also the saturation region is important to understand what happens during the switching. So we'll need to keep all those conditions into account. In terms of time spent, the transistor are typically on in the ohmic region or off. But in practice, but if we think in terms of the impact on the performance of the digital circuits, the saturation region is important. Okay. Of course, this is the Nmos. For the Pmos, the situation is pretty much similar. What are the main differences? Of course, we have a different threshold voltage. For the Pmos, the threshold voltage is negative, okay? And the Pmos is in the on state if the overdrive is negative. So this means that the VGS, the voltage between the gate and the source, must be more negative than the threshold voltage, which means larger in module but with a negative sign. Therefore, we can write the before we write, just let me add something. So this is the threshold voltage. For this Kn constant, of course, in the case of a Pmos, we will have a Kp constant that will be defined more or less in the same way. The only difference is the term related to the mobility, because of course in the Pmos we will have mu p, which is the mobility of holes. So more or less these are the only two things that are different. They have an impact. Let's look into some detail. So let me write briefly the situation for the Pmos so that we all have in mind the same thing. We have a VTP which is smaller than 0. Then we have an off state if VGS is larger than VTP. Larger means also less negative. Then we have an ohmic region if VGS is smaller than VTP, of course, but also VDS is negative by definition in a PMOSFET, is larger than VGS minus VTP. Okay, when I say by definition, I mean that in a MOSFET, you know that the drain and the source are identical terminal from the physical point of view. In the case of N MOSFET, we call drain the terminal at a higher voltage. In the case of P MOSFET, we call drain the terminal at a lower voltage. It's just a definition. Okay, this should be clear. Basically, you know that I don't want to let's say to repeat again and show you the, let's say, a picture of a MOSFET, but we have seen some figures also together. They are completely symmetrical. So the drain and the source must be defined in order to be identified. Okay. So just let me add a note here. So in this case, we are in the ohmic region, I already wrote, and then we have something like this. EDS is equal to Kp times VGS minus VTP times VDS minus VDS squared. Okay, so the same identical expression. We should be careful with the sign here, because this VGS minus VTP is negative, VDS is negative, so this is negative. Yeah, so the product is positive. This is negative, so totally this term within square brackets is positive. So with this sign, IDS is positive. Typically, since the terminal at a higher voltage is the source, we can write something like this. So this is the P MOSFET, this is the source, this is the drain. If we call IDS the current between the drain and the source, in a P MOSFET, IDS becomes negative because current flows in the other direction. So I add a minus here. Okay, because otherwise it becomes positive. Or we have to write here ISD, but it's just two. Or we can write something like this. No, it's the same. Of course, it's the same. Then, again, we know what is Kp. Kp is W over L times mu P times epsilon R epsilon aux over T aux. This part is the same for the PMOS and the NMOS, because during the fabrication process, the gate oxide is deposited at the same time on the PMOS and on the NMOS transistors. So this part is identical by fabrication. Okay. So the only part which changes is the mobility of holes, hole mobility. Then we have the saturation region. in which we write the same thing. Minus IDS is equal to Kp over 2 times VGS minus VTP squared. So, another thing that you probably know, that for the inverter, but also for the other CMOS logic gates, we have a perfectly symmetric behavior between the pull-down network and the pull-up network. And there's a simple thing that we can do if we want to have let's say, maintain a symmetric behavior between the low state and the high state of a logic gate. Let's consider it in the case of the inverter. And if you look at these IV characteristics of the PMOS, and you look at the same characteristics of the Nmos, you see that you can have perfect symmetric behavior of the PMOS and of the Nmos if just two conditions are satisfied. If Kn is equal to Kp, and if Vtn is equal to minus Vtp. Because in that case, basically, apart from the sign, the behavior of the curves, the behaviors of the curves are the same. So we have just two parameters. If these two parameters are equal, except for the sign, we have basically identical curves and a symmetric circuit. We call it a balanced inverter. If Kp is equal to Kn and Vtp is equal to minus Vtn. Of course, in this case, the sign has to be different by construction. So, one thing that is important is that we always try to be in this situation because it's convenient for many reasons. I will describe some of them, but let's keep in mind that we want this situation to happen. Okay, in this situation, the behavior of the PMOS is perfectly symmetric to that of the Nmos. So for this reason, we call the inverter balanced. This thing is obtained by looking at the expression of the K constant. If you look at the expression, they are very similar. There are some things that are identical, and so we can, let's say, remove them, but others are not. So Wp over Lp times mu p epsilon r epsilon o 0 over Tox must be equal to Wn over Ln times mu n epsilon 0 epsilon r over Tox. Okay, I added here to W and L this subscript P for the PMOS and N for the Nmos, just to distinguish between them. And of course, as I was mentioning, this part is identical to this part. We cannot modify them because by fabrication they are identical. The mobilities are different for electrons and holes. And if we want to have a balanced inverter, we have to compensate for the difference in mobility by changing the geometry. And actually, what we do is we change the width. Of course, you already know that because I've seen the program. You know how is the sizing of a CMOS. logic of that. Just I want to go again over these concepts. Why we touch W? Because typically it's very convenient for us to use the same L, and this is typically the minimum L allowed by the process. For several reasons, and the main two reasons are power consumption and speed, we need to use the lowest possible L in digital logic. So we keep these two quantities equal, and therefore we use WP times mu P equal to Wn times mu N. So what does it mean? Traditionally, we have WP in silicon, at least. In silicon, and of course we're talking about silicon, traditionally Wn is about twice WP. Mu N is about twice mu P. This is basically a property of the material, so it's only something related to silicon. And for the crystalline structure of silicon and for the property of the element, we have that electrons travel faster than holes, have a higher mobility. It's 2 times, sometimes it's even close to 3 times. It really depends on the material. Let's put 2 in our case. This means that we keep WP in order to compensate about twice Wn. So we use wider P transistors. Okay. For the most modern Cmos technology, actually things have changed. Basically you have more or less the same mobility for electrons and holes. Okay, let's say it's something that is true from 2012, okay, in the last 3 years, and therefore there's no reason to use different widths. Okay, so it's only in the most aggressive CMOS technologies that we have more or less the same mobility for electrons and holes. What's the reason for that? I mentioned something during the first day we met, basically, and it's the strain applied to silicon. As I've told you, in the last few years in CMOS fabrication process, in order to improve the performance of the CMOS transistors, we have applied strain to silicon, so tensile strain for NFETs and compressive strains for PFETs, and this strain improves the mobility of both electrons and holes, and in practice improves the mobility of holes much more than that for electrons, so that more or less they have the same mobility. This is a big improvement, because basically this means that you can make the NFET with the smallest possible width, and therefore also the PFET with the smallest possible width. And so the total area occupied by the logic can be smaller. So in the end, it's a big improvement in terms of area occupation. Before you had to make large PFETs, now you can make the PFET as large as the NFETs. Okay, this is the reasoning for the K constant. For VTP and VTN, basically this balancing is obtained with doping. So the doping of the N channel and of the P channel is done in such a way as to let's say, equalize the two threshold voltages. Okay. Now, we can now consider the transfer characteristic of the Cmos inverter. Again, I try to highlight only the things that I really need in the following. Of course, you have already drawn the characteristics. This is V out as a function of V in. Of course, we sweep V in from 0 to VDD, and we have V out from VDD to 0. So for convenience, I redraw the inverter here. You see that V in is equal to VGS of the NFET, and is equal to, this is the S, the source of the PFET, this is the gate of the PFET, so V in is also VGS plus VDD, VGS of the P transistor plus VDD. So what can we write here? For the Nmos, if V in is smaller than VTN, the Nmos is in the off state, right? So this is VTN. In this part of the quadrant, the Nmos is in the off state. Okay. Now we have to distinguish between saturation and ohmic region. You remember that we are in the ohmic region if VDS-N is smaller than VGS-N minus VTN. Okay? This means VDS, if you look here, is V out, and VGS is V in minus VTN. Okay? So V out smaller than V in minus VTN. So we can draw the line with the equal sign instead of the minus sign. Of course, is a line which has a slope of 1, and when V in is equal to VTN, has V out equal to 0, so passes through this point, right? Below, when we have the smaller sign, we have this situation, so ohmic region. So we have, say, Pmos off. Here we write Pmos ohmic region. Okay, and of course, in the other situation, we have the Pmos in saturation. Okay, so I took a quadrant, and then I have divided the quadrant in 3 regions. I've partitioned, actually, the quadrant in 3 regions. In each region, I can define the bias condition of the sorry, of the Nmos. I wrote Pmos, but I'm talking about the Nmos. Just it's difficult to talk and to write at the same time, and okay, one makes confusion. You need to talk, to write, and to think on what you have to say after, and then one makes confusion. Okay, this is for the Nmos. Then we can look at the Pmos. I change color so that we do not make too much confusion. Okay, so we do the same thing. We try to partition the quadrant for the Pmos, right? Again, off state. Of course, the off state is if VGS-P is larger than VTP, okay? In this case, VTP is negative. VGS-P, you see here, is Vin minus VDD. So, this means Vin minus VDD larger than VTP, which also, of course, means Vin larger than VDD plus VTP. Okay? In this situation, the Pmos is off. So, VTP is negative. We can consider this point to be VDD plus VTP. So this means that this distance is the module of VTP. Okay? For Vin smaller than that, larger than that, the Pmos is in the off state. So in this in this region, this ribbon, the Pmos is off. Okay? Then we have to find the difference between ohmic region and saturation region, but it's easy because in the ohmic region, VDS-P, which is negative, is larger than VGS-P minus VTP, as we wrote in the previous slide. So VDS-P is this distance, is V out minus VDD. Okay? V out minus VDD is larger than VGS-P, which is V in minus VDD minus VTP. Okay? So at this point we can cancel out VDD and VDD on both sides. And then we have V out larger than V in minus VTP. So again, this is we can draw the line which corresponds to the equal sign, and this is a line with a slope of 1, which passes from a point here at minus VTP, because when V in is equal to 0, V out is equal to minus VTP. So this is the line, and above this line, for the when the larger sign is true, we have the ohmic region. So Pmos in ohmic region, and here we have the Pmos in saturation. Okay, so again we have divide. Of course, V out cannot be larger than VDD, so we have a quadrant is not a complete quadrant, it's a square of side VDD, both directions, but we have partitioned the whole space. Now we are ready to draw the IV characteristics, which is something that is already known to you, but let us do it again. So let's start from the situation when B in is equal to 0. Then of course we are in this situation, and therefore the Nmos is off and the Pmos is on. Can be in ohmic region or in saturation, but of course is on. And this means that V out is equal to VDD, because current cannot flow, so there's no voltage drop between the drain and the source of the Pmos, and therefore V out is equal to VDD. We start from here. Then we increase V in, and of course what happens is that the Nmos is always off, and therefore the Nmos is always off. The Pmos is in the ohmic region, and therefore the output voltage is equal to VDD, because only this Pmos is in the on state. There's no current, so VDS is 0, right? So we are in this situation, right? This is easy to draw. Basically, the output voltage is exactly equal to VDD. Let's call it 1. Then, when V in becomes larger than VTN, something happens, because the Nmos goes from the off state to saturation, right? So the Pmos is in the ohmic region. You can see here. So what happens? Of course, what happens is that currents can flow from VDD to ground. Okay? If current can flow, we have a voltage drop between the source and the drain of the PMOSFET, and therefore V out starts to go below VDD. Okay? You have to consider this situation. Of course, the PMOS has a lower resistance than the Nmos, because it was basically, because it's in the ohmic region, it was basically short-circuited. So what we start to see is that gradually V out decreases from VDD. Decreases from VDD, because this Nmos starts to conduct. Okay. And this is the second part of the region. And I stop here because, of course, as you can see, something happens here. Anytime we cross one of these dotted lines, there is a change in the bias condition of one of the transistors. So we have to stop and to look at what is happening. Okay? I'm not interested in, let's say, obtaining an analytic expression for the formula. But of course, it would be easy, because the Pmos is in the ohmic region, and we know the expression. The Nmos is in saturation region, and we know the expression. Then we can, let's say, that you can say that the two currents are equal. Okay, and by imposing these conditions, we can extract the curve which relates V out to V in. Okay, it's something that it's easy in principle, because it's a mechanical exercise. Okay, one just needs to make the calculations. If you try to do it, you see you obtain an implicit expression. It's difficult to make it explicit, but it's useless, because this is the shape we obtain. So we're not interested in the exact analytic expression, also because the expressions that we have used up to now are approximate. So there's no reason to obtain them precisely. But then we are here. Now something happens. There's a change in condition. The PMOS goes from the ohmic region to saturation. So in this part, we have both the PMOS and the Nmos in saturation. So we have current flowing from VDD to ground. You can see, when I say current flowing, I of course am meaning that the inverter is dissipating power, because when inverter is in the on state, in the 1 state or in the 0 state, of course, one of the switches is open and therefore there's no current flowing, at least in principle. But in this 2 branch of the characteristics, in the 3rd branch of the characteristics, we have both the transistors in an on condition, and therefore we have power consumption. Of course, this is important because power consumption is the most critical issue for digital electronics. It's the most critical issue since 40 years. Okay, now, well, let me first draw the line here, and then I will explain what is actually happening. Basically, we have a very steep drop of Vout. This is almost a line, a straight line, not a vertical line, but a straight line. Okay, I would like to spend some time on it because there is something we can do, which is easy but also pretty accurate. You know that when a transistor is in the saturation region, you can use the small signal models. The small signal models that you have used during your course in digital electronics are only valid in saturation. Okay. Now we are exactly in that situation because both transistors are in saturation. Let's try to use the small transistor models here. Let me use the next line. What's small circuit model? Small signal model. Small circuit model of the Cmos inverter in region 3 of the transfer characteristic. So this is V in. These are the gates. The gates are at the same node. Gn is the gate of the N MOSFET, Gp is the gate of the P MOSFET, right? Then this is ground. Of course, the source of the N MOSFET is ground, but also from the point of view of small signals, also the source of the P transistor is at ground because it is at VDD at a constant voltage, right? Now, this is VGSN, and then for the N MOSFET we have a current generator, a controlled current generator, which is GMN times VGSN. And then we have the output resistance RON, the output resistance of the N MOSFET. And this is the drain of the N MOSFET, which is also coincident with the drain of the P MOSFET and is also the output voltage node. Again, we have the same thing on the other side. We have GMP from drain to source of the P MOSFET times VGSP, and in parallel we have ROP. So this is the simple small circuit model. Of course, things can be adjusted a bit because this source of the P MOSFET is at the same node of the source of the N MOSFET, which means that the two current generators are actually in parallel, and also VGSP is equal to VGSN, and they are both equal to V in. So basically we can redraw everything here and write something similar. We can write a single current voltage generator, controlled current voltage generator, which is GMP plus GMN times Vin, and also ROP is in parallel to RON. ROP in parallel to RON. You see now the circuit is much simpler. We can write V out over V in as minus GMP plus GMN times ROP in parallel to RON. We can call this part A0. So minus A0. This is the voltage gain of the inverter when the transistors are in the saturation region. In this particular condition, and therefore, of course, in this case, V out and V in are small signal, are the small signal component of V out and V in. If we go back now, that ratio V out over V in this case, these are the large signals, so that ratio is just the slope of this part. So this slope is minus A0. Okay? This is the slope. Is that clear? So basically, let me repeat this concept. This is the small circuit model. So I'm saying that the variation of V out over the variation of V in is minus A0. If I go back to the large signals, this means that if I say again the variation of V out over the variation of V in is minus A0, I mean that the slope of this curve is minus A0. Okay? So the slope of the characteristics is the gain of the inverter when both transistors are in the saturation region. Then we can continue. Then now it's easy. When we continue, we cross this dotted line, and therefore the Nmos goes from the saturation region to the ohmic region. So this means that we still have current, but then now we have a smaller drop on the NMOSFET. So we start to go in this direction, and at some point here we have that the PMOS goes off. Here the PMOS goes off. This means that we have no current anymore from the supply voltage to ground, and therefore the voltage drop between the drain and the source of the NMOSFET is 0, and therefore V out is 0. So we close in this way. So this is 4 and this is 5. So we have drawn the complete line. Now, I've shown you before the condition in order to have balanced inverter. When we have a balanced inverter, something interesting happens in this transfer characteristic, which means that this transfer characteristic is perfectly symmetrical. Because of course the PMOS and the NMOS are symmetric. VTN is equal to minus VTP, so the one part of the characteristic is equal in length to the 5 part of the characteristic. The 2 and the 4 are equal, and the part 3 is in the center of the square. So this point in the middle of part 3 goes from VDD half on the x-axis to VDD half on the y-axis. This is something that happens if So let me just add this, if the inverter is balanced, and this is something that we want. This is only happening if the inverter is balanced. Of course, since this characteristic is symmetric, also the noise margin for the high level is equal to the noise margin for the low level, and therefore also this is good from the point of view of noise margins. And it is something that we want. Okay. Now, for the moment we have looked at the static characteristic, so at what happens when we apply an input voltage and we want to know the output voltage. When we have the transfer characteristics, of course we know for any input voltage what is the corresponding output voltage. Now the other important thing is understanding what happens from a dynamic point of view. So what happens when we change the input voltage? What's the time needed in order to observe a change in the output voltage? Because this time is something that is related to the speed of the digital circuit, and therefore to the clock frequency at which we can run the circuit. Okay. In order to do that, we need to evaluate the propagation times of the inverter and in general of logic gates. But we will just focus on the inverter because the concepts that we see on the inverters are the same concepts that we can see in the other logic gates. So let's look at the propagation delay. The propagation delay, it's usually called TP, and there are two different propagation delays for an inverter. Typically you have the TP from high to low of the output and the TP from low to high, that in principle are not the same. So this is the situation in which you have this transition, this is the situation in which you have this transition. So let me remind you the definition of propagation delay. So in order to evaluate the propagation delay, we have to consider the dynamical situation. So we have time-dependent behavior of the input voltage and of the output voltage. So let's assume that the input voltage changes between the high and low level, between the high and the low level a few times. What we observe in time is that V out does the same, but of course with some delay, because V in changes and then after some times also V out changes. The change is not instantaneous because there is, of course, in practice there is some charge that has to be moved. So, for example, this is the behavior of V out, and considering this plot, we can define the propagation delays. In order to define them, what we do is the following. We fix the VDD level, then we fix the VDD half level, and we draw the corresponding horizontal line. Okay, now let's look at the transitions. When you have the transition from high to low of the output, this is the transition from high to low, we will define as propagation delay from high to low the time that passes from the moment in which the Vin is equal to VDD to the moment in which the Vout is equal to VDD during the high to low transition. So this distance in time is Tp h to low. And of course, when you have the transition from low to high, we measure the propagation delay as the time from the instant in which Vin passes through VDD half to the instant in which Vout passes through VDD half. Tp low h. Why they are important? Of course, they are important because the time period of the clock has to be, of course, larger and typically much larger than both the Tp high to low and the Tp low to high. Because, of course, you cannot, let's say, change the states if the output of the different logic gates have not settled yet. So T clock has to be higher, sometimes much higher than Tp, then than the max between Tph to L and Tpl to H. So it is important to keep both of them under control. The lower we can make them, the faster we can go. And of course, the most performing is the digital circuit. Now, what we should do now is connecting this part to the quantities of the transistors that we have already written in order to understand what's, for example, the effect of the channel length on the propagation delay, what is the effect of the supply voltage on the propagation delay. So we need to be more quantitative here, and let's make this calculation. Let's, for the moment, compute the propagation delay from high to low of an inverter. So, for simplicity, we can assume that the transition of the input voltage is instantaneous, and we only look at the transient of the output voltage. So, what we do is the following. We apply an ideal generator to the input so that we have an instantaneous transition. This is Vin. Vout, of course, is equal to VDD. This is Vout that is equal to VDD. And then we start to observe the transition. Exactly what is happening. Basically, we have this inverter here. By the way, I don't remember if probably I should just stress these symbols that I'm using. Okay, I use this symbol without arrows for the Nmos and this symbol for the Pmos without the arrows because they are easier to draw. You probably have used it also in the I've seen that in the notes the symbols that are used are always the ones with the arrows. But then, I mean, these are simpler to draw. Just, okay, let's consider this just an instruction, a legend. Now, so what happens here? When we switch Vin from 0 to VDD, the Nmos goes in an on state, and the PMOS goes in the off state. So basically, we can immediately neglect the PMOS. We basically have only, let's assume that we have an output capacitor as a load. We need to discuss this issue, but let me discuss the load later. We assume that we have an output capacitor, because I'm putting an output capacitor because we typically have at the output of an inverter another logic gate which has as inputs the gates of other MOSFETs, and therefore can be seen as a capacitor. Okay, but I will come back to the exit value of C. Now, we can forget about the PMOS, because when Vin goes to VDD, the VGS of the PMOSFET is 0, and then the PMOSFET goes in the off state. And there we are left with this situation. We have an NMOS with VDD between the gate and the source, and a capacitor which at Vout at T equals 0 minus is equal to VDD, because at the beginning the output voltage is VDD. So we have to decrease the output voltage, and in order to decrease the output voltage we have to discharge this capacitor. Okay? And the capacitor is discharged only through the NMOSFET. So let's consider first the situation at T equals 0 plus. Okay? At T equals 0 plus, of course, the output voltage, which is the voltage on the capacitor, has not changed, so is equal to VDD, and this is the VDS of the NMOSFET, and the Vin at T equal to 0 plus by construction is equal to VDD, and this is the VGS N. Of course, in this situation, VDS is equal to VGS, so VDS N is larger than VGS N minus VTN. And therefore the transistor is in saturation. Okay? So at 0 plus, the transistor NMOS is in saturation. This is useful because we know the current. The current is equal to EDS, which is also the current which is discharging the capacitor, is equal to Kn times Kn times VGS N minus VTN to the second power. But VGS N is equal to VDD, so we can write 1/2 Kn VDD minus VTN to the second power.